And I'm Kozlowski. I'm a software engineer at Singleton. I've spent the last 2 years or so working on highly performant APIs in Ruby. High performance in Ruby typically aren't phrases heard in the same sentence. But we've had enormous success using Goliath without having to sacrifice the ease of coding with ActiveRecord. So before we get too far into things, a little background on the API that we had to scale is necessary. It's called the ring pool API. The ring pool API allows you to track calls similarly to how you would track a web click. You pass us a unique set of parameters, and we'll give you a unique phone number back. And if that phone number gets called, it shows up in reporting and allows you to make more intelligent decisions about where you're spending your marketing budget. Internally, a ring pool is a collection of phone numbers. The customer can have many ring pools, so usually attached to a particular marketing campaign. And each ring pool will contain between 200 and 500 numbers. To protect validity of call attribution, we reserve a phone number for a preset period of time after each allocation. This requires some architectural consideration because there are times when a customer will request a number against a ring pool that doesn't have any available. It's all locked out. So, to ensure that we always have one to give out, each ring pool has an n+1 number that we call the overflow. We'll give it out if you don't have any other numbers available. We don't track any call attribution data with it. In some extreme situations, we've seen these overflow numbers handed out several hundred times a second. And so, there's no way to correlate it with an incoming call. So we were approached about 2 years ago by a client who wanted to use the ring pool API that had much higher throughput requirements than our Rails stack was going to be able to support. Our existing API, the old Rails stack one, could support per connection about 5 requests a second. We got one phone number per request, and the round-trip 90th percentile response time was about 350 milliseconds. The client requirements were a little bigger. They wanted to handle at least 1,000 requests per second per connection. They wanted at least 40 phone number allocations per request, and they wanted a round-trip total response time to 90th percentile less than 200 milliseconds. So, some quick back-and-back math, that's an 8,000-fold increase in throughput just for a single customer. So, well, the requirements were pretty clear. We needed very predictable low latency, and we needed to be elastically scalable as we brought more users onto the network. Additionally, we wanted to leverage our existing API, so we knew that the new system needed to be able to communicate with the old system asynchronously. We also knew that eventually we were going to want to share the business logic, all the complex stuff that we had over in our main app with this new API and other APIs somehow. And so bonus points if we could find a solution that was in Ruby. So while Ruby brings a lot of awesome to the table, there are some considerations necessary when you start thinking about highly performant applications. The main thing that we were working about, because we're on the Metz interpreter, was the global interpreter lock. For most dynamic languages, this is like the elephant in the room. It's worth noting that neither the JRuby nor the Rubinius interpreters implement a GIL, and so they don't have this issue, but who is running Rubinius or JRuby? Okay, so it's still a problem for most of us. So in short, the GIL is a wrapper placed around every Ruby statement, and it prevents the process from consuming more than one CPU. It's nice because it simplifies the interpreter's design because the implementers don't have to think about multi-threading, and it prevents a lot of data consistency issues that can pop up in highly concurrent code. The downside is that since we can only run one Ruby process per core, we can't write truly parallelized applications. In the ideal world, this is what your CPU usage would look like. You'd have one application running, and it would evenly spread its work across all the available CPUs on the machine. However, with the GIL, you end up totally pegging out one process and then just leaving the rest doing absolutely nothing. So the only way to get around this in the MRI, at least, is to run multiple cooperative Ruby processes. So we sharded our API across cores. The second issue we needed to address was, it's called the C10K problem. The idea that the question is, how can we best optimize our application to handle 10,000 synchronous incoming requests? We could write highly threaded Ruby code, but that's really difficult to get right. Or we could avoid that complexity entirely by using the Reactor Pattern. The Reactor Pattern is one solution to the C10K problem, the one we chose. The gist of it is that whenever we're writing code that would block the main thread, referred to as a reactor, like an HTTP request or a database insert, we toss it on the bottom of the queue with an asynchronous callback, and pull the next action off the top of the queue and start working on it. The application then selects for events for which the blocking I/O is completed, and runs the callback serially. This allows us an optimal level of concurrency without having to multi-thread. If We've seen Node.js, that's the Reactor Pattern in JavaScript, in Python, it's a twisted library, and in Ruby, the Reactor Pattern library is Event Machine, which you may have heard DHH notice as keynote. This is an example of what a call to a remote API would look like in Event Machine. For any action we expect to block, in this case, queries to Facebook and Foursquare, we define a callback for when the request succeeds and an airbag for when the request fails, one of which will be executed when the action completes or unblocks. Unfortunately, in many cases, the callback and airbag might be 80% similar. At Invoca, we have another API that runs on Event Machine, and these callbacks make the code really difficult to read, write, and test. Without very careful architecting, our code was becoming incredibly brittle and nearly unintelligible. You can end up with a complete mess of spaghetti code. If you've worked in Node.js, this might be very familiar to you. Fortunately, because Ruby, there is a better way. Synchrony is a gem that sits on top of Event Machine, and it leverages the fibers introduced in Ruby 1.9 to make writing asynchronous code much easier. Instead of using callbacks, when a method blocks the reactor, its state is stored in the fiber stack, and the reactor moves on to the next event. When the fiber unblocks, when the reactor unblocks, or when the method unblocks, the reactor resumes it from the stack. Synchrony handles all of the complicated stuff in the background and lets us program linearly and without fear of being arbitrarily interrupted. This pattern of application scheduling using fibers, also known as coroutines, will be familiar for any of you who are working in Go. This is identical to Go routines. Linear code. So instead of this potential pile of smells and confusion, we ended with something that looks a lot more like the kind of code that we enjoy writing and testing. We wrap blocking code in fibers, and Synchrony handles the rest. So enter Goliath. Goliath is a Ruby web server that leverages Event Machine Synchrony, and the async rack, and handles each incoming request as a separate fiber. All asynchronous I/O will transparently suspend and later resume without us having to do any of the heavy lifting. You define a response method that takes a single argument through which Goliath gives you all of the request data, do whatever work you need to do, and return the result to Goliath to ship over the client as an HTTP response. This last non-blanked out line here is the array that you hand back to Goliath. Position 0 is a status code, in this case 200. Position 1 is the headers that you want to give back, in this case nothing. And position 2 is the body of your request. So using Event Machine, Synchrony, and Goliath enabled us to build a really performant system. But Colin's going to illustrate the difference between threaded and reactor pattern Ruby code, and then talk some about the software design decisions that we found to be very effective in asynchronous Ruby programming.
All right. Thanks, Dan. You guys ready to see some code? Always my favorite thing. All right. So.
Not going to that meeting.
No. So,
where is that thing? We name all of our conference rooms. The fishbowl is all glass, so it's kind of a fishbowl.
So at the bottom level here, I've got a very simple web app that just counts. It does nothing but count. So here's the threaded version of the code. Then if you've written threaded code, you'll recognize you would have a new text to protect it. You've got a state variable and a counter. Down here is the increment method. We do that inside the new text. We've got a special case when we want to shut down, set the state and stop. Here's the counter itself. When you want to retrieve it, you also grab the new text, so you have a safe copy of it. Here's my run method. When I kick this thing off, all it does is create a thread. And then get stop. And down here is increment forever. This is the actual heart of the app. Here it just increments until rest to stop. So there's a simple threaded version. Here it is evented. I basically deleted a quarter of the code. There's no need to mess around with mutexes because you're not going to be asynchronously interrupted. So it's much simpler to reason about. The only difference down here is fiber.new instead of thread.new. And this little piece actually kicks off the fibers. They do it in 2 steps with fibers, unlike threads that are run immediately. And so down here I had to do one other thing. Because this happens to be a CPU hog application, I did need to periodically yield. This is fairly rare that you would have giant chunks of CPU, but this is the downside with writing cooperative code. You have to cooperate. So here I've set every 100,000 really hard and pause. All right, and then here is the actual app itself. This is the little Goliath app. By the way, this is all up on GitHub. We get the link at the end. So here's the actual server. It inherits from the Goliath API. It gets set up with a counter object. I've got 1 to 2 counters that will be passed in. Do a little bit of startup here and then run the counter. And then this is the actual heart of the web server. Every request comes in. These are the paths in the URL, right? So the /counter hands back this little bit of JSON. We've also got isAlive if you're connected to an ELB or other load balancer. We have a way to go live. And here's the 404 handle. It's that simple. There's also a async Sinatra if you wanted to do more complex web stuff. Yeah, a little bit of code down here at the bottom. Look at the command line to decide which type of counter to run, and then this is the boilerplate actually get Goliath running. So let's fire this thing up. I've got, let's see, this one here. Let's see here.
Hotkey? Use maybe down. There you go, cool.
Alright, so in one window here, I'm going to run the threaded one. And in the other window, here, I'm going to run the evented one. So there's evented, there's threaded. I'm going to give the threaded one a head start. And here's the evented one. Alright, so I've got the log coming out right to the screen here. So those are the live logs. So those things are running now. And down here in this window, I'm going to hit both of those. One's running at port 9000 and one's at 9001. So they both start at 0. And to see the speed, the evented one is more than twice as fast. And that's because it's not messing around with mutexes and it's not being asynchronously interrupted. So also you might notice they happen to always be multiples of 100,000 in a single network. And that's exactly what you'd expect because it's cooperative, multi-threaded. The only time it's going to have a chance to serve my /counter action here is when the fiber was moved. All right, so that concludes that demo. I think 2x is more than 2x here. I think 1.5x would be a more typical kind of number you can see on the overlap. This is obviously kind of degenerate, but significant difference in density. Okay. So I want to talk a little bit about some of the software design decisions that we made that really seem to pay off in building this API. So, to start with, Synchrony supports many popular ActiveRecord stores, including MySQL. Use MySQL 2 driver for that. Postgres, Mongo, Redis, Memcache, MQP, all of those. And there's plenty of third-party drivers as well. Typically very, very small patches to have them work with Synchrony. Biggest problem we had was dependencies. When we pulled in ActiveRecord code like this, the autoloader in Rails kind of encourages, or at least enables, dependencies between models. In this example, my dependency in the user of the count is actually okay. Rails doesn't force the count to be loaded there. But as soon as I mentioned email address in user, it pulled in the email address class, and then that class mentioned network, and pulled that in. You mentioned a gem, we'll pull the gem in. So we had to spend a fair amount of time snipping dependencies. And we ultimately went with turning off the autoloader entirely in our Goliath. We really wanted to pick just the models that were actually necessary to be pulled in to our server. You probably know ActiveRecord is fairly slow. So for maximum density in your API server, CPU hogs include loading objects. It's fairly slow. Validations and callbacks can add up. So TLDR, use thin models. Models with few dependencies and few validations were the best fit. We also found we needed to encapsulate handling of exceptions. So we have a gem that we put together. This is open source up on GitHub called Exceptional Synchrony. And it's just a layer that we added above event and synchrony. It has a couple shims, most important of which maps exceptions across callbacks. I'm going to show that. We've also got a proxy that sits in front of the event machine just to make the methods a little safer, and parallel sync layer that helps with parallel. Each of those in turn. So here's the way we do callback exceptions. To start with, this is a straight event machine example. You've got a callback and an airback, and you may notice connection.close appears in both places. This is off the Pete code event machine tutorial, I think. And that's typical for callbacks and airbags. It's not a natural way to code. You wind up with some degree of duplication. Right there. It's not dry. So one of the things that drew us to Ruby was that it has out-of-band exception handling, raise and rescue, similar to throw and catch in C++. We really found that to work great to keep your error handling separate from your go-write code. So here we can see that Synchrony unified the return path. This is the version that's using Synchrony. We no longer have an airback and callback separated, but the single result is being sent back into that request, and then the code is doing an if-else. This reminds me of coding in C. You kind of hope that your fellow developers might remember to check return codes. It's not a great way to build really reliable code, in my opinion. So, inspired by a piece of Synchrony code, we realized that we could tunnel exceptions over to callback. By doing that, there's no need for a separate airback. So, here's the ensure callback method in this gem, and it just calls that return exception private method down there, and it's very simple. It just takes the return value or an exception, whichever happens, you get that back. And that's what we send across. So we call it a success in all cases. It doesn't really matter because you're going to pop right out. On the other side, where we have a layer, this fairly clumsy long name here, but map deferred result. And it takes those results and knows how to check them. And if they respond to his exception, it will raise them back. So those two put together, you get right back to straight, linear, plain old Ruby code. You can see here now what we had to do was ensure that the connection gets closed on the way out. Exactly like we expected. One thing I wanted to mention here as well, for testing, we often found we could unit test these things without any of them. That this is linear code that will run perfectly fine without all the machinery involved in starting up the line. That was never true for our event machine projects. Unit testing them was quite difficult.
You always had to start the reactor before you do any testing.
Yeah. Okay, and speaking of exceptions, the exception gets loose when a event machine or Synchrony fiber calls into your code, your process will exit. That is not any fun, and we learned this the hard way. We had some of our server processes fall over and get restarted by a process manager. It seemed to be random. We eventually got to the bottom of it, and it was friendly fire. It was internal exceptions, often for very mundane things. You know, the file commission wasn't right or something, something like that, and blew up and shut the whole machine down. So after having been burned by that, we wound up with just a thin layer above all the event machine methods, and they look like this. They just rescue and log the errors and don't let them get any higher, because these are basically the top of the stack. There's nobody above you at this point, if you let the exception get up to them. They'll exit. All right, you might notice that this is actually rescuing the exception, which you ordinarily wouldn't do because that is the lowest level exception. It will even rescue like a script error if you have a typo. But when you have an always running API server, that's actually exactly all right. So event machine proxy wraps all these methods, basically all the top level methods from event machine. All right, and the last piece to talk about in this gem is parallel sync. Evented code is natural for writing in parallel, but makes it hard to write in serial code. Coroutine libraries like Synchrony reverse that. Serial code is easy to write, it's trivial in fact, but when you want to run code in parallel, you need to take some explicit steps. So here's the heart of our API's scatter gathered across the shards. You'll see that it says responses equals, and then it kicks off this parallel block. And that adds all the work to be done to talk to the other shards. And then when you hit the end of that block where the comment is there, all of the results are going to rendezvous there, and it's available now as an array to be used in the next statement. This really should be a future promises pattern. We're working on that. I'm going to try to work some other gems in to get that to work the same. I also want to call attention to the last line there. It's a plain old Ruby object without even a hash. We use those extensively, and I'm going to talk about them a little bit. So we call them immutable value classes. They're plain old Ruby objects that you would use instead of a simple string or hash typically. We found this to be a great pattern inspired by Sandi Metz. You'll see here we have an initializer that sets the object up. In this case, it holds the array of responses and also what format. You'll notice the design by contract enforcement here that we don't allow formats except those two. In fact, these days we don't even allow XML. But I left it in there just to show the point that it's a great pinch point for contract enforcement. There's no accessors or writers. This is read-only. That's the immutable part. If you want to change it, you change a copy. That's the convention. These classes typically don't serialize themselves. Someone echoing the previous talk. So in this case, the JSON knows how to serialize itself as an array of responses, and we've got a matching method from JSON, which is a factory method there. We found this pattern to work out great. So these things are all unit tested as individual pieces. They're composable. If this had been a hash, which is the typical way this kind of code would be written, yeah, hash does have to JSON, but it turns out that it almost never has exactly what you want in JSON. As soon as you have some internal bookkeeping that's different than what you want to share with your external clients, a hash would not work. Right? And so it turned out the bulk of our code wound up being in these immutable value classes. So that was pretty neat to see it go like that. So these were Sandi Metz's rules. We actually read about them after we did this project the first time, but they nicely point out, direct you toward plain old Ruby objects, and I particularly recommend the immutable style. It isn't required, but it's great for functional programming, and it was also perfect for concurrency because Ruby is a shared reference language. We'll have many requests coming in at the same time, and if they were mutating data structures, even though with fibers they won't happen asynchronously, you still have to worry about anything you do with blocks. When you come back, the data structure might be different. And the simplest answer is don't change them. So I would be very, very, very happy if there were a functional Ruby out that flat out made that the rule. And we found that by using these classes, we naturally decomposed into much smaller pieces of code in avoiding big monoliths. All right, the last piece I want to talk about briefly is Singletons. I don't mean the eigenclass style Singleton, I mean the global variable Singleton. TLDR is very evil. They're global variables. You can't control their lifetime, you can't pass constructor parameters, you can't reuse them, you can't easily test them. And Singletons beget more Singletons. They're hydras. You start into those, you get more and more of them. So we have a modified Singleton pattern that's worked great for us. This is an example class that is what keeps our secrets, the credentials we use to talk to other third-party APIs and such. It's similar, it's got an initialize method, but you notice it's actually allowed to take a constructor parameter. It's making its dependencies explicit. Turns out, after we wrote the code this way, about a month ago, we actually had a case that we needed 2 secrets files, and this code worked great. Where the Singleton pattern would have been dead in the water as soon as you needed 2. Down here, you'll see there's a method to set any particular instance to be the global one, and a class method to get at it. So you still have the convenience of getting at things without having to pass them through if you need it, but you also have all the flexibility and address all the shortcomings I listed. Okay, hand it back to Daniel.
Cool. So we also learned some important lessons about architecting large concurrent systems in the cloud. The first of which was about TCP latency. So this diagram shows the handshake that's performed each time a TCP connection is established. It's performed to determine the bandwidth of the connection. but if you can see the x-axis, this handshake can take about 20 milliseconds. On the left side here is HTTP 1.0. Each time the client wants to send a request, they open a new HTTP connection, perform the handshake, send a single request, get a single response, and then close a connection. Rinse and repeat. Given our SLA, losing 20 to 30 milliseconds to a handshake on each request was highly undesirable. Fortunately, HTTP 1.1 introduced connection persistence. Subsequent HTTP requests are pipelined across the initial TCP connection. The slow start handshake is performed once, and the connection is kept open for as long as it's needed. So we used HTTP 1.1 persistent connections to communicate between shards, and further optimized communication between shards on the same server by using domain sockets instead of TCP connections. One issue that we did run into was with ELBs, Amazon's Elastic Load Balancers. They can only forward requests to a single port per server in rotation. So we had to put an AJ proxy instance on each API server in order to round robin requests to the individual shard processes running on that server. This is what the setup ended up looking like in EC2. The client hits an ELB, which round robins to the available HA proxy instances, which in turn round robin to local API shards. The receiving shards send requests to other shards for ring pools that they don't own, and then the initial receiving shard consolidates the responses into a single JSON body and returns that to the client. Ring pools are assigned round robin to API shards to balance load. The system also allows us to move more heavily trafficked ring pools from one shard into a second that's experiencing a lower average load. So what happens when a shard falls over or doesn't respond in time? Initially, we implemented what we called the watchdog. It would monitor the API shards and react quickly to reassign ring pools if one shard stopped responding. However, we didn't like the complexity in that design. I mean, who's going to watch the watchdog? So instead, we taught each shard the overflow number for every ring pool in the system. So if a shard doesn't respond quickly enough to an allocation request, we just hand back the overflow number. We also rate limit communication between shards. If one shard notices another shard is taking too long to process a request or respond, we start handing back overflow numbers instead of actually hitting the slow shard. Over time, the shard that noticed one shard was being slow starts to allow more and more requests through instead of handing back overflows all the time. So we took these measurements from EC2 using JMeter, which ended up being a fantastic tool. With 3 JMeter instances slamming our API, we had about a 93 millisecond median, 90th percentile, 124 milliseconds, and we were able to process 1,400 requests per second. 4 JMeter instances slamming the crap out of our API. We had a median of about 102 milliseconds and a 90th percentile of 144 milliseconds, and we were able to process 1,700 requests per second. With 5, we were able to process 2,000 requests per second. We found, awesomely enough, and as it shows, the bottleneck was the number of requests that JMeter was able to hit us with, not our API. We later found that we could have used AWS's VPCs to ensure that data goes through Amazon's private backbone as opposed to going over the public internet, and that would have cut an additional 10 to 15 milliseconds off of each round trip. So the final result exceeded the SLA with a fair amount of headroom. So fun fact, there are 5.5 billion phone numbers in North America. At this rate, we could allocate every North American phone number in less than 12 hours. So it was a tremendous success. We were very, very pleased with the results. So some other tools we used Minitest and Factory Girl. Our entire test suite runs in less than 10 seconds. We used simple coverage to make sure we weren't being lazy. And that's 10 seconds with a 99.96% coverage ratio. And again, as mentioned, Apache JMeter for load testing was awesome. You can run it headlessly up in the cloud. Very easy to consolidate results. It's very easy to create very unique and complex testing sets for it and share those with clients who are also load testing against our API. We got a couple of shout outs. We'd like to really thank the maintainers of Event Machine and Event Machine Synchrony. I personally would like to shout out to the IRC channels Ruby and Ruby Lang on Freenode. We'd like to thank Google Labs and Ilya Grugoric, who are the maintainers of VM and VM Synchrony respectively. And a shout out to Sandi Metz for a lot of the best practices that really made this project possible. You want to do that one?
Yeah, I've got a call to action here. I would strongly encourage you to try Goliath as a stack for your mixed API server. If you have any questions, feel free to hit us up on Twitter. We'd love to help out. I think it's a really great stack, and I'd love to see a version in the future of Rails itself. I know Ilya Grugoric was proposing that idea in 2011 or so. It didn't quite happen, but I think it should have. And now that we heard DHH mention Event Machine as being part of Rails 5, I would love to see Synchrony as well. So I'm going to see if I can help out with that project and try to steer it that way. But it'd be a great stack together with a fin, for instance, which is already built on Event Machine. We would get a lot more density and take a little bit of the momentum away from Node.js, which is really kicking asses when it comes to density. All right, so that's the end.